Hello, my name is John Evans. Welcome to this video on Rietveld refinement. So what I want to go through in the video is on the screen here. I want to go through a simple example of doing a Rietveld refinement using laboratory powder X-ray diffraction data on a simple metal oxide, yttrium oxide, using the Topaz software suite. Before we do that, I want to go through some of the basic ideas and the equations that lie behind Rietveld refinement so that we understand what we're doing when we use a software package like Topaz. We'll look at a little bit at the anatomy of an input file, how we set up a command file for doing a Rietveld refinement. We'll look at different ways of defining and refining parameters using that input file. We'll look at a couple of other files, topaz.log and topaz.inc, which tell us how that refinement is actually working. Towards the end of the video, we'll look at peak shape functions, the mathematics of the equations that we actually use to describe peak shapes in the powder diffraction pattern. And as we go through, we'll look at some simple equations in input. There'll be some later follow-up videos on some more specialized topics using this example, things like how to archive the results of the Rietveld refinement when we've finished, how to describe the peak shapes more efficiently, refining unusual parameters, and maybe some other things as well. So what I'm going to assume as we go through the video is on the screen here. If you want to follow the video yourself and go through the example yourself, you're going to have Topaz Academic or the commercial version of Topaz installed on your computer. You'll need to install JEdit, and there's a separate video on how to install JEdit and set it up to work with Topaz. You'll need to download the data files. I'll put a link in the comments at the bottom of the screen on where you can find those data files. I am going to assume that you've done a course on crystallography, so you know what a diffraction pattern is and you know how diffraction works. And I'm going to assume that you know what a powder diffraction pattern is. Just in case you don't know what a powder diffraction pattern is, here's a cartoon of a simple powder diffraction experiment. You would have some source of radiation, typically monochromatic X-ray radiation. You fire that at a polycrystalline sample, and then you move a detector in blue here through an angle of 2 theta around the sample, and you measure the diffracted intensity. So this might be a typical powder diffraction pattern at the bottom. It's a plot of the diffracted intensity in counts as a function of the diffraction angle, the Bragg angle, 2 theta. So the blue are the experimental points. Now we're going to be talking about Rietveld refinement, and before I start, if you want a simple introduction to Rietveld refinement, you can try this paper in the top left of the screen here. But what we're going to be doing in a Rietveld refinement is we're going to be trying to extract quantitative information from our experimental powder diffraction pattern. And to do that, the process is we will have some kind of a model. And from our model, we calculate what we would expect the diffraction pattern of that model to be. And we compare it to the experimental data. At the end of a Rietveld refinement, what we would hope is our calculated diffraction pattern, which are shown in red on the screen here, follows or looks just like the observed diffraction pattern, which are shown as blue points. That will be a successful Rietveld refinement. So if we're going to do that process, I think we need to know something about where the information is stored in a powder diffraction pattern. And if we're talking about crystallography, the information is stored basically, I think, in 3 different places in a powder diffraction pattern. So the first place is where the peaks are sitting, so the 2 theta values of the reflection. So we label reflections in the powder diffraction pattern according to their Miller indices, their HK and L values. So on the right here, this is the 440 reflection. Now the position of that reflection primarily determined by the size and the shape of the unit cell of the material. So Bragg's law, lambda is 2d sine theta, relates the 2 theta value of the reflection to its d spacing, which is determined by the unit cell parameters. There are often smaller effects, little aberrations due to the experiment, which can shift slightly, and we'll look at those in a second. The second place where information is stored on the left here is in the intensity of the peaks. If we've got a single crystallographic phase present, then the relative intensities of the different peaks in the powder diffraction pattern are determined by the positions of the atoms inside the unit cell. So if we're after structural information, the structure of the material, it's the relative intensities that are going to give us those fractional coordinates and therefore the structure of the material. That's if we've got a single phase present. If our powder diffraction pattern is of a multi-phase sample, so more than one phase is present, then the relative intensities of the peaks of the 2 different phases can actually give us quantitative information on how much of each of those phases is present in our sample. And again, that can be very useful. So that's the basic place where information is stored in terms of intensities and positions. The third place where there's information is actually in the shape of the peaks in the powder diffraction pattern. Now, the shape of a peak in a powder diffraction pattern is influenced by a number of factors. It's influenced by factors caused by the instrument that you use, source of radiation that you use, but also some factors due to the sample. So particularly things like the microstrain in your sample or the size of the crystallites in your sample, particularly actually the diffracting domain size of the crystallites in your sample, and things like stacking faults and other forms of disorder in your material influence the shape of peaks in a powder diffraction pattern. So there's actually a wealth of information about microstructure in peak shapes, and we'll look at that in some later videos. So that's the basic idea about where the information is stored in a powder diffraction pattern. Let's just look at a few of those things slightly more mathematically, as I say, just so that we understand how Rietveld refinement works. And let's start with the positions of a peak in the powder diffraction pattern. How do the Miller indices tell you where you would expect the peak to be? Now, of course, that's given by to us by Bragg's law. So if we've got a material with a certain unit cell, on the right of the screen here, I've shown a cubic material with a cell parameter A. The d-spacings of H-scale reflections from that unit cell will be given by a relatively simple formula. So this is the formula here for a cubic material. The formula for a material with a different symmetry, say a triclinic unit cell or an orthorhombic or a monoclinic, will be a different expression. It will be slightly more complicated, but there's always a simple geometric expression that lets you relate the H, K and L values to the cell parameters, calculate the d-spacings of the reflection. And then once we know the d-spacings, we can use Bragg's law on the left here. Lambda is 2d sine theta to calculate the diffraction angle theta, or double it to give us 2 theta, the Bragg angle that we're normally interested in. So we can always calculate the Bragg angle that we would expect for a given H-scale reflection. Now in practice, we'll nearly always observe that the experiment will nearly always find that the experimentally observed 2 theta values are slightly different to the ones that we calculate. And that's due to a number of aberrations, which I've expressed in the equation on the screen as a delta 2 theta value. So we see a small shift in the 2 theta values away from where we would expect to see them. So those shifts can be caused by a number of factors. Probably the two most important ones are at the top here, the 0-point alignment or the sample displacement. So the 0-point error is to do with the fact that when you do a diffraction experiment, you set your detector to a nominal 2 theta equals 0 position. But if the diffractometer is slightly misaligned, when you set a value of 2 theta, it might not be the actual value of 2 theta of the beam going through the diffractometer. So you would have to correct for any offset when you do your Rietveld refinement. To be honest, in most modern lab setups, the 2 theta point on instruments is really very well defined. And what's normally causing the peak shift is a sample displacement error. Again, if you're doing a reflection geometry experiment, then the 2 theta value is actually determined by the height of the sample in the diffractometer. If the sample is slightly too high, peaks move to higher values of 2 theta. If the sample is slightly too low, they move to lower values of 2 theta. So nearly always it's a displacement error that you should be refining in your Rietveld refinement. There are some other effects that cause peaks to shift. Things like sample transparency or beam divergence can cause peaks to be very, very asymmetric, and that can shift their 2 theta value a little bit. And then there are more subtle effects due to, for example, a sample being flat in a Bragg-Brentano experiment, whereas it should really be curved to match the radius of the diffractometer. So various aberration terms can affect your observed values of 2 theta. You need to take account of those during the Rietveld refinement. Okay, so that's peak positions. What about peak intensities? Well, peak intensities are governed by the 5 terms in the expression that I've given at the top of the screen here. So let's just look at each of those terms in total. So the first term in the intensity expression is the scale factor. And that's to do with the fact that when we calculate a powder diffraction pattern in a Rietveld refinement software package, we're calculating it on some internal scale. And then we need to multiply that pattern. We need to scale it up or scale it down to fit our experimentally observed intensities. And we'll always need to refine the scale factor. And you can appreciate that if you think, for example, if you record a diffraction pattern for a certain amount of time, and then you double the amount of time that you record it for, you'll need to double your scale factor to multiply the model onto the experimental data. So that's the scale factor term. The second term is what's called the multiplicity term. And that's to do with the fact that traditionally, when you're doing a powder diffraction calculation, if you had a cubic material, you might, for example, choose to calculate the intensity of the 100 reflection. But then you know by symmetry that, for example, the 100, the 010, and the 001 reflection all have the same intensity by symmetry. So you would typically multiply that intensity up by an appropriate factor to take account of those symmetry equivalent reflections. The third term is called the Lorentz polarization correction, and that's a term that corrects your calculated pattern for the geometric factors of the diffractometer that you actually use for the experiment. So the typical expression for a lab diffractometer will look something like the blue equation on the screen here. And for example, it contains a term which describes the 2 theta angle of the monochromator that you're using if there's a monochromator in your experiment. So most lab experiments will need an LP factor something like the expression on the screen. If you've got a different geometric setup, you might need a different LP factor. Then maybe the most important term if we're doing crystallography is this term in green here, which is called the structure factor for a HKL reflection. And the reason why the structure factor is particularly important is it contains the information about the fractional atomic coordinates. So remember, if we're doing crystallography, what we're trying to find out is the fractional atomic coordinates X, Y, and Z of the atoms in the unit cells. They appear in the structure factor expression here, X, Y, and Z. And they're multiplied, of course, by the H, K, and L values, the Miller indices of the reflection. And those tell you the 2 theta value where you find the reflection in the diffraction pattern. Okay, so the next terms in the structure factor expression here are the ones in brown and purple. Fj is the atomic form factor. Remember, in an X-ray diffraction experiment, it's the electrons on the atom actually interact with the X-rays and give rise to diffraction. So you need to tell the Rietveld software what atom you've got sitting on each site in the crystal structure so it can use the correct form factor. Now, the intensity diffraction from any site depends on what atom sat at the site, but it also depends on the fractional occupancy of that site. So frequently you find in lots of inorganic crystals particularly that sites aren't fully occupied. So it might be that a site is occupied in one unit cell, but in another unit cell it's empty, and that gives rise to a fractional occupancy. And again, we've got to take that into account when we calculate the structure factor, and it will feed into the overall intensity. So those are the two terms in brown and purple. And then the final term at the front is what's called the Debye-Waller factor, or the temperature factor. It turns out in any atomic crystal, atoms are never stationary. They're always vibrating around their mean position. And that vibration actually smears out the electron density of that site, and it causes the intensity to be reduced. And the mathematical form of the reduction is shown on the screen here. What we refine in our Rietveld refinement is a quantity called the temperature factor, or the atomic displacement parameter, B. And the intensity fall off is given by minus B sine squared theta over lambda squared. So what that does is it ends up making the intensities weaker, and particularly they get particularly weak high angle. So the higher the value of the temperature factor, the greater the reduction intensity due to this Debye-Waller term. Okay, there are various other corrections that we need to think about now. Deliberately in this tutorial, we're going to be using some simulated diffraction data. So if you like, it's a perfect diffraction pattern, so we don't have to worry about these effects. But in real samples, we might need to worry about effects like preferred orientation or texture in our sample. We might need to worry about the absorption of X-rays by the sample, or extinction in the sample, or even in some experiments, the intensity of the incident beam might change as a function of time. In real materials, there are various other corrections that we might have to worry about, but we won't have to worry about them today. Just while we're on this slide, I want to think about one other factor that we're going to encounter when we do our Rietveld refinement, and that's the problem of correlation between parameters. So by correlation, what I mean is that the value that we extract for one parameter might be influenced by the value of another parameter. And one place where that's particularly important is in considering temperature factors and occupancies during a Rietveld refinement. And people may often say to you that you can never refine site occupancy and temperature factors on the same site because they're highly correlated. What do they mean by that? Well, what they mean by that, we can think about if we think about a simple example. Let's imagine that for a site in a given crystal structure, we've made that site fully occupied. It's 100% occupied by a certain atom. Now, in reality, it might be that that site is only 50% occupied. But how would our Rietveld refinement compensate the bad assumption that we've made? Well, if you look at the temperature factor and the occupancy, they appear in the structure factor equation as a product. So if we've got the occupancy of an individual site too high, what the Rietveld refinement might do is it might try and reduce this temperature factor term to compensate for that error. And if you think about the expression for a temperature factor, the way to reduce this term Tj would be to make the value of B higher. So if we've got the site occupancy of a site too high, we might expect the temperature factor to refine to a larger number than it should. If we had the occupancy too low, we might expect the temperature factor to refine to a smaller value than it really should. So the temperature factor and the occupancy can be very, very highly correlated parameters in the Rietveld refinement. Now, it turns out they're not completely correlated because actually the temperature factor term you can see from the red expression actually has a theta dependence to it. It varies as a function of 2 theta across the diffraction pattern. If we've got very high quality data over a large 2 theta range, you might be able to refine the site occupancy and the temperature factor simultaneously. If you've got lower quality data over a narrow 2 theta range, you have to be very, very careful, and we'll explore that when we look at the example. Okay, so those are the main equations that lie behind Rietveld refinement. Now, of course, when we're doing a Rietveld refinement, what we're trying to do is, if we look at the picture on the right, we're trying to make our calculated diffraction pattern fit the blue observed data as closely as we possibly can. And the process we normally use for that is a least squares process. We do least squares refinement. And so what we do in a least squares refinement is we try and minimize this quantity at the top of the screen here. What we try and do is we minimize the weighted squared differences between the observed and the calculated experimental points. So if we look at this little zoom picture on the right of the screen here, we've got our calculated pattern in red, our observed data in blue. The difference between the two is this little pink arrow here. So for each point in the diffraction pattern, we take those differences, we square them, we multiply them by a weighting factor and add them up to give this quantity here. We try and minimize this quantity during the refinement to make it as small as possible. Once it's as small as possible, we've got the best possible fit between our calculated pattern in red and our experimental pattern in blue for the model that we're using. So to follow a Rietveld refinement, again, we'll see this when we go through things together. The best thing to do is to actually look visually at how your calculated pattern and your experimental pattern match up with each other. It's also useful to have some numerical indicators to tell how well your model fits your data. And the one that's most commonly used is this one in the middle of the screen here. It's called the weighted profile R factor. It's a particularly useful quantity to follow because it's directly related to the quantity that we minimize. The weighted profile R factor is given by this equation in the middle of the screen. It's the weighted sum of the squared differences between the observed and the calculated intensities, divided by the weighted sum, the sum of the weighted squared observed intensities. So the way that R factor is set up means that if you've got a bad model, your calculated and observed data are very, very different. That will be a large number. If you've got a good number, it will be a small number. Now, typically we multiply that by 100 to quote the R factor as a percentage. So what we ought to see is our R factor decreasing as the refinement goes on. People often ask, well, what's a good R factor at the end of a refinement? Actually, that's an impossible question to answer because the R factor at the end of a refinement depends on the quality of the data that you're analyzing. But just ballpark, if you've got a good laboratory powder diffraction pattern, you might expect an R factor of maybe 10% or so at the end of the refinement. An indicator that's slightly better to follow is what's called the goodness of fit, which is related to the chi-squared of the fit. And the goodness of fit is defined by this equation at the bottom of the screen. It's actually the weighted profile R factor divided by the statistically expected R factor. It's given by this expression on the right here. And it contains two additional terms. It contains the number of data points that we're analyzing and the number of parameters in our model. And again, the way that that statistic is set up is at the end of the refinement, if you've got an appropriate structural model and all of the errors in your fit are random rather than systematic, then that quantity ought to tend to 1 at the end of the refinement, because your weighted profile R factor should be equal to the statistically expected value. Okay, so I think those are all the equations that we need to understand to follow a Rietveld refinement. So what we'll do next is we'll switch to my desktop and we'll go through a simple Rietveld refinement example together. Okay, so here we are on my desktop. What I've got open is a folder that contains 2 files. It contains a file called demo02.xye. That's the data set that we're going to be analyzing. If I open it up, it's just a text file. It's got values of 2 theta, the observed intensity, and the standard uncertainty on that intensity. As I said, it's actually simulated data, so we don't have to worry about experimental artifacts, but we're going to be treating it as if it's a experimental powder diffraction pattern. The other file is a crystallographic information, or a CIF file. It contains the basic information about the structure that we're going to be analysing, which is Y2O3. It's a cubic material with a cell parameter of about 10.55 angstrom. Its space group is IA bar 3, and at the bottom of the file, these are the fractional atomic coordinates, or a guess of the fractional atomic coordinates for this material. So let's do a Rietveld refinement. If you've looked at the other videos on JEdit and Topaz, you'll know the first part of this already. We're going to open a program called JEdit, which should appear on my screen any second. So here's JEdit. It's just a text editor, and this is a window where we can type in simple text commands. If we want to do a refinement, Rietveld refinement with Topaz, we're going to open these insert menus, and there's some menus here called the Topaz Durham menus. I'm going to open those and I'm going to work through the menus for doing a simple Rietveld refinement. So I'm going to double click on select data file. I'm going to select the data set that we want to analyze, which is demo02.xye. I need to tell Topaz something about the instrument that we use so that it knows the correct LP factor to apply. So the data is appropriate for what's called the Durham D8 diffractometer. I'm going to refine a 0 point to allow for any offset in between the observed and the experimental 2 theta values, and I need to read in a CIF file. So I'm going to read a CIF file and select from the correct folder, which is this one. I'm going to select the CIF file we need to analyze. Okay, so that should be a basic input file for a Rietveld refinement setup. Let's just go through that file and have a look at it, and I'll just tidy it up a little bit as I go. So at the top of the file here, we've got a line which contains information about the various R factors, and that will get updated after the refinement. So here's the weighted profile R factor, and here's the goodness of fit for the refinement that we're doing. There's some general information to Topaz about how to do the least squares refinement next. This line here, iters 100,000, tells Topaz how many cycles of least squares we want to be performing. For a simple refinement, we can probably just do 100 cycles of least squares as the maximum number. The next line here, chi-squared convergence criteria, that tells Topaz when to complete the refinement. So if the chi-squared of the refinement, which is related to the goodness of the fit, changes by less than this number in each cycle, then Topaz will assume that the refinement has converged and it's appropriate to stop the refinement. So the next set of information in the file is about the data set that we're analyzing. So we've got here the name of the experimental data set. We need to tell the Rietveld refinement we will be calculating the model pattern at different values of 2 theta, and we need to tell Topaz what values to calculate the model or powder diffraction pattern as. So the default thing, and what this line says to Topaz, is look at the experimental data, look at the 2 theta obs values, and calculate the model at the same values of 2 theta. So the next line here is describes the background polynomial to fit the intensity in between the diffraction peaks, which in a standard crystallography experiment we're not really interested in. And we're going to use this as simple polynomial. I'm going to turn the refinement of that polynomial off to start with, but this would be a 6th order polynomial. It would have 6 coefficients as a function essentially of a constant plus 2 theta squared. It's set up mathematically slightly differently, but that's the basic idea. The next line here, simple axial, is going to be describing asymmetry in the peaks. And again, just to start the refinement off, I'm going to fix that parameter to a value of 0, and we'll look at the effects of that parameter later on. The next lines in the input file describe the diffractometer that we're using, the LP factor that we need to describe. And the data that we're using is appropriate for a D8 diffractometer, which was set up with a germanium 111 monochromator. And the monochromator angle was set to 27.26 degrees to theta, which gives us pure copper K alpha 1 radiation. The next line here is the 0 point error, the offset between the actual value of the detector and the true 2 theta 0 value. So I'm going to fix that quantity at 0 to start with. So the next section in the input file describes the structure. So the keyword here is str, and that tells Topaz structural information is coming next. We've given our phase a name of Y2O3. It's got unit cell parameters A, B, and C of 10.55 as the starting model. Its base group is IA R3. The fractional atomic coordinates are listed here, and the site occupancies are here, and what atom is on each site is here. So that tells Topaz what scattering factors to use, and the value of the isotropic temperature factor or displacement parameter is at the end of the line here, 0.5 angstroms squared. The scale factor is listed next, and I'm just going to turn off refinement of the scale factor to start with. And then this line at the bottom of the file here describes the peak shapes. We'll come back to that later in the refinement. But for now, I'm just going to fix the values of the instrument parameters to the default values that were read in by JEdit. And we'll see later whether those are appropriate or not. So that should be everything set up to do a simple Rietveld refinement. And there are no parameters turned on. So Topaz should just do a single calculation of the model pattern and compare it to the experimental data. So we're going to click on this button here, which sends the file to Topaz. When we click on that, it will give the file a sensible file name. It's the name of the data set, then the word read appended, and then a serial number, so we can update that as we try different models analyzing our data. I'll save that input file. I then click on this TA button, which should launch Topaz on my computer, and Topaz appears. It appeared on my other screen, so I've dragged it across, and this is the basic Topaz window that we'll be working with, and the name of the file that we're trying to work with, the input file, is written in this button on the right. So if I click the run button, Topaz should try and do a Rietveld refinement. It's told me on my screen, it's done the Rietveld refinement. It says on the screen, do I want to update my input file with the results of the refinement? Now, I haven't actually refined any parameters, so I'm just going to click yes at that point. And we can see what's appeared on the screen is in red is our calculated pattern. In blue, we can almost see it as the experimental pattern, and in grey is the difference pattern. And just to start with, I'm going to turn off the difference plot so we can see things a little bit more clearly. And if I zoom in, you can just about see that the experimental pattern is here and the calculated pattern is here. There's some resemblance between the observed and calculated patterns, but it's not very good at the moment. And we can see that, for example, if we look at the R factor of our refinement, it was 7,600%, so a big R factor. Okay, so let's go back to the input file. And one of the parameters that's nearly always turned on by default in a Rietveld package is the scale factor. So that's what multiplies the calculated pattern so it matches the experimental pattern. So normally when you do a Rietveld refinement, the scale factor would be turned on. So let's turn that parameter on and just do a Rietveld refinement. I should say as we start, we're going to go through this Rietveld refinement step by step. If you've looked at the other video on the mechanics of working between JEdit and Topaz, you'll know that the least squares algorithms in Topaz are sufficiently stable that probably with this particular case, I could just turn on all of the parameters of importance and it would converge to the right minimum. But we're going to go through things stepwise so you get an idea of some of the pitfalls and some of the things to think about. Okay, so let's think about refining the scale factor. And let me do that just by pressing this step button. And what that will do is a series of cycles where every time I press the step button, I'll do a cycle of least squares refinement. So I start off with an R factor of 7,600%. And as I do another cycle of least squares refinement, the R factor comes down to 3,800%. You can see this plot here is showing how the R factor is changing. When I do a series of least squares refinement cycles, the R factor comes down very nicely. If I keep clicking that button, the R factor has come down to 99% on my screen here. But if you look at the screen and we zoom in at what's happened in the Rietveld fit, can you see that essentially what's happened is the calculated patterns more or less disappeared from our screen. So what the least squares is doing is it's something that's mathematically sensible, but as a chemist or a structural chemist, it doesn't make a lot of sense to us. What's happened is the scale factor is just reduced to try and make the red line match the blue line as closely as it possibly can. And the only way it can do that is basically by reducing the scale factor. So essentially the crystallographic phase that we're interested in has disappeared from our calculation. Now, if we accepted the results of this Rietveld refinement and went on and tried to refine other parameters like the peak shapes or the unit cell parameters, we would probably find that the refinement would diverge because essentially our phase has got a close to zero scale factor. So in a case like this, I would probably say, I don't want to update the input file with the results of this refinement, but I want to think about things a little bit. And this is actually quite a common problem that you find when you're starting with the Rietveld refinement. You start with a model that looks reasonable, but as you refine parameters, the model diverges, and if you like, your fit seems to disappear. And it's often that you're refining parameters that in the wrong order, and so the model is diverging. So I'm going to click no here, and I'm going go back to my input file, and instead of refining the scale factor, just to start with, I'm just going to change its value. Now, the calculated pattern was far too intense. I'm going to reduce the scale factor by putting an extra 0 in there, sending this to Topaz, and let's do the refinement again. So if I do the refinement again, and I will accept the results of that refinement, can you see now that the calculated pattern and the experimental pattern are on roughly the right scale? And that's true across the whole diffraction pattern. So let's just work with a fixed scale factor for a moment. Let's think about what's wrong with the Rietveld at this point. Well, clearly, if we look at the Rietveld refinement, the calculated pattern in red, the peaks are offset relative to the experimental pattern in blue. So the 2 theta values are wrong. And we know from the discussion we had earlier that the things that affect the 2 theta values are the unit cell parameter primarily, and then any calibration errors in the diffractometer. So we can see that the peaks are too high 2 theta values. And if we think about Bragg's law, lambda is 2d sine theta, that probably means that the unit cell parameter is smaller than it ought to be. So let's just go back to our input file, and let's just try changing the unit cell parameters. So they're 10.55 here. Let me just try making them 10.65, seeing what happens. So if I just do a single cycle of least squares with them at 10.65, I accept that. Can you see now that the peaks are too low? So that suggests that the cell parameter is larger than it ought to be. So let's try a value halfway between the two. Let's try 10.60, and then seeing what that does. And with the cell parameter 10.60, actually we're doing a pretty good job fitting the peak positions at that point. Okay, so if we look at things now, what we actually see is the peaks are actually slightly offset to the right of where they ought to be still. So that's the peak at low angle. And let's look at high angle. The peaks are slightly better at high angle, but certainly at low angle, they're offset relative to the experimental positions. So let's try a 0 point offset. Perhaps there's a calibration error on the diffractometer. And just for the sake of argument, let's go back to the 0 point, and let's make that value say minus 0.1 degrees for the sake of argument. See what that looks like. If I try that, I can see that actually the peak positions are matching up more closely with the experimental positions at low angle, and they're reasonable at high angle. So maybe at this point we could actually try refining the 0 point error on the diffractometer. So the 0 point error is actually stored in what's called a Topaz macro. And with the Topaz macro, there are various ways of turning the parameter on and off. If the parameter's got a name with an exclamation mark in front of it, it tells Topaz that that's a fixed quantity that you don't want to be refining in the least squares refinement. If you want to turn that parameter on, you could just delete the exclamation mark. So now if I go back to Topaz and do the refinement, if I just press this step button, we can see at the top of the comments here that the number of parameters that we're refining is 1. That's a 0 point parameter. And if we do the refinement and go back to JEdit, we'll find that that quantity is actually refined. Because it's a refined number, it's now colored in red. If I want to fix that parameter again, I can turn it back to an exclamation mark. Now when I go back to Topaz and I run through the refinement and I come back to JEdit, that quantity is still there in the refinement. The 0 point is still being applied, but it's now a fixed quantity, and so it's colored in blue. You don't have to give a parameter a name in a macro. If you just leave that blank and go to Topaz, then again, that will do exactly the same thing. The same 0 point is applied, but it's not refined. If you don't want to go to the trouble of giving a parameter an actual name, you can just use the @ symbol, and that just tells Topaz to assign a parameter name to it. So when we do the refinement now, the 0 point is refined again. If we do the refinement to come back to JEdit, it's colored in red. So there are various different ways of working with these macros. Quite often when you start doing more advanced things in Topaz, you might want to come up with your own equations during the Rietveld analysis. So what happens when Topaz runs is these macros actually get expanded into fundamental equations, which are the actual equations that Topaz is applying. And if you want to look at those equations, there's various ways you can do it. If we open the X-insert menu and we go to the help folder, there's a file called topaz.log that gets written in your main Topaz directory every time you do a refinement. And that file actually contains these expressions expanded into a basic mathematical language. So let me just, so things are easier to find, let me just give the 0 point parameter name again. I'm going to call it 0. I'm going to rerun the refinement and then go back to JEdit. And now I'm going to open this file called topaz.log. And so what topaz.log is, it says at the top of the file, it's what's called an expanded input file. And as I say, the basic macros in our input file get written out into more fundamental language. So if we scroll down through this file, you can see that there's a line in this file where the macro for the 0 point has been expanded by defining a parameter with the name of 0. And then at the end of this line, this little equation written, which says that the 2 theta offset that Topaz is going to apply is equal to the value of this parameter 0. So that's the fundamental mathematical equation that's being applied. Again, if I go back to my input file, instead of using a macro, what I could do is I could define a parameter called 0. So param 0, I'll give it a number, minus 0.03. It's always useful when you're defining your own parameters to give them some kind of a minimum and a maximum range to make sure that they can't diverge to silly values. So let me just say that the minimum possible value of the 0 point would be maybe minus 0.1 degrees, and the maximum possible value would be plus 0.1. And then I'm going to write an equation that the 2 theta offset to apply to our calculated pattern is equal to the value of this parameter called 0. And you put a semicolon at the end of an equation in Topaz. If I put colon 0, what's going to happen is at the end of the refinement, the value of this equation is evaluated and it's written in the input file. So this should be another equivalent way of refining the 0 point. So let me send that to Topaz and run that through. We get exactly the same fit as we had before, but this time using a parameter that we've defined ourselves. This is one of the beauties of Topaz. It gives you flexibility to define your own parameters and apply them to the model. Okay, the final place that it's often useful to look if you want to understand Topaz in a bit more depth is a file called topaz.inc. Now the macros in Topaz are actually defined in this file called topaz.inc. So if I open topaz.inc, again, it's just a text file, but it contains the Topaz macros. So if I do a search in there for the word 0, what you'll find is a macro defined, and it's actually defined at this point. The macro zero error is actually renamed as a macro called ZE, and then ZE itself is this expression here. So the macro, you can see the basic equation that's applied here. So that's the equation that we've just been working with. The syntax in these macros is a little bit complicated the first time you see it, but you should be able to work through and get a basic idea of what's going on. Just while we've got this file open, let's just look for one other macro. Later in the video, we're going to be looking at peak shapes and powder diffraction, and we're going to be using what's called a TCHZ peak shape. And we won't go into any depth now, but the peak shape that we're going to be using later in the tutorial is actually defined as well as a macro in this file. So the peak shape macro that we're going to be using is this macro here, and the equations that get applied by Topaz when you use that macro are written out in Topaz.inc. Now, they're complicated equations. We don't need to really understand any of the detail of them now, but just so that it brings some bells later on, just look at this equation here. We'll come back to it later in the video. This is saying that the Lorentzian component of a peak shape, PV underscore law, is given by some equation which depends on a term q squared, and q to the power of 3. I'll come back to that later in the tutorial and we'll see what those actually mean. So let me shut topaz.inc. Let me shut topaz.log so I don't get confused in a moment, and come back to our input file and turn it back to the way it was before we started playing with equations. Okay, so where have we got to? We've got to the point where we can now, we've got a reasonable 0-point error and an okay fit to our diffraction pattern. Let me just zoom out on our diffraction pattern. Actually, let me just reset Topaz and run again. And here's our whole diffraction pattern. So we've got a reasonable fit to our diffraction pattern. Probably what I would do at this point is turn on a few parameters. I would probably turn on the unit cell parameter so it refines at the same time as a 0-point error. If we want to refine the unit cell parameters, because it's a cubic material, A is equal to B is equal to C. If we give all of those parameters the same name, their values will be kept constant during the refinement. And just so I don't forget in a minute, I'm going to turn the scale factor back on. Let's do a few cycles of least squares. Okay, so with those parameters refining, I'm now getting a better fit to my diffraction data. My R factor is 82.753. And again, if we go back to the input file, you'll see that the cell parameters have refined and they've all got exactly the same values. Now, again, with cell parameters, you might say to yourself, well, this is a cubic material. Why am I defining 3 separate parameters, A, B, and C in my input file? But it turns out you don't need to do that. Again, in Topaz, what you could do, and the way that I normally work, is the B and C cell parameters for a cubic material. I normally just write a little equation that says the value of the B and C cell parameters is equal to the value of the A cell parameter with a little equation. So if I set things up like that and do the refinement, then I go back to Topaz and my A, B, and C cell parameters are again equated to each other, but it's maybe a simpler way of working. There is, of course, a macro which you can use to describe cubic cell parameters, where you just need to give one number in that macro. Okay, so here's our Rietveld refinement. Let's just zoom in and look at the refinement. We'll turn the difference curve on, and let me just look at a portion of the refinement out at high angle. So what we see if we look at the diffraction pattern now is we can see quite clearly that some of the peaks are calculated with too low an intensity, and some of the peaks are calculated with too high an intensity, for example, the one on the right here. So what affects the relative intensity of peaks in the powder diffraction pattern, of course, is the fractional atomic coordinates. So let's come back and look at the fractional atomic coordinates. Now, the fractional atomic coordinates of this material are listed here. And some of these coordinates we're free to refine. Some of these coordinates are fixed by symmetry. So we need to decide which ones we can refine and which ones we can't. Now, I happen to know that in this example, I can refine the X coordinate on yttrium 2 and the X, Y, and Z coordinates on oxygen 1. But if I didn't know that information, how do I check that? Well, there's a couple of things we can do. One thing that's going to be useful is we can add a little command to Topaz called num_positions. and that tells you the multiplicity of each site. And so if I put num position 0 and I do a round of least squares refinement and I go back to my input file, the multiplicity of each site has been updated. So that tells you that if you've got one atom on the first position, it generates 8 atoms in the unit cell. So that's a quick way of checking the composition of our sample. So this material is Y2O3, so we can quickly see that the cell contents are 8 and 24, 32 yttrium atoms and 48 oxygen atoms. So it's yttrium 32, O48. If I divide through by 16, Y2O3, so the chemical composition of the material is correct. Now these labels are related to the multiplicities of the Wyckoff site, so whether it's an 8A or an 8B site. So we can always look up which fractional atomic coordinates are free to refine using international tables. So for example, for this site, a quarter, a quarter, a quarter, we might expect it's a special position. We could check that in international tables. There are various resources online if you don't have international tables handy. The one that I've just started using is on the IsoDistort website. So IsoDistort is a wonderful website for exploring symmetry. It's run by Brenton Campbell and Harold Stokes. And one of the things on the IsoDistort site now is it's got a suite of programs. One of them is called ISO Space Groups, and you can see it's new. It's just been put online. If I go to ISO Space Group, it basically lets me select the name of my space group. So the space group we're working in is space group 206, which is IA bar 3. So if I come down to that space group, there are various options about the origin of the space group, the different settings, but I can just come to the bottom and click OK. And it gives me a list of the Wyckoff positions for that particular space group. So for example, we've got an atom on a quarter, a quarter, a quarter, which is an 8B site. And we can see that that's a special position. We can't refine the value of a quarter away from where it is. The other yttrium atom is actually sitting on a 24D site, which I've highlighted here. And you can see that that 24D site has actually got a free coordinate, the X coordinate, free to refine. So you can always check which coordinates you can and can't refine by looking on the web or looking in international tables. So as I say, Topaz makes you do this work yourself. Other Rietveld software handles this for you, but the philosophy in Topaz is the user should decide that, because sometimes you might want to break those space group conditions and deliberately allow an atom to refine off its ideal site. So if we want to refine the site coordinates, one thing we can do is give each of the parameters, each of the values, a parameter name. So one easy way to set up parameter names is to name them according to the site label. So if I do a control and drag my mouse in JEdit, I can highlight a column of text. If I do control C on the keyboard and then come to the coordinates and hold down control and highlight a single column, I can type X control V space. And each of those X parameters has now got a parameter name. Here I can do Y control V space and name each of the Y parameters. And here I can do Z control V space and name each of the Z parameters. So as we said in this particular example, the X parameter is a fixed quantity. We can't refine it. The Y on yttrium 1 is fixed and the Z on yttrium 1 is fixed. The X value of yttrium 2 we're free to refine. Its Y value has to be fixed and its Z value has to be fixed. Oxygen, we're free to refine its X coordinate, its Y coordinate and its Z coordinate. So we can give all the parameters names and very quickly set ourselves up to refine the fractional atomic coordinates. Okay, so let's take that and we'll send that back to Topaz. And we will do a few cycles of least squares. So if I do a step, 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 and then refine to convergence, can you see that now our pattern of intensities is matching the observed pattern really very nicely as we've refined those atomic coordinates. We might notice now that if we zoom into the pattern, actually one thing that's not fitting properly is the background of the calculated pattern isn't going through the experimental background points. And that's because we haven't yet turned on the background polynomial. So let's switch the background polynomial on to refine. Let's send that to Topaz and let's click to do some least squares refinement. So now the background of our calculated pattern is going through the experimental points. If we unzoom, we've got what now looks like a really quite nice Rietveld refinement. Okay, let's zoom in and have a think about what we need to do next. Well, the thing that's clearly wrong at the moment in this Rietveld refinement is that the calculated peaks are much sharper than the experimental peaks. So we need to do something about the calculated peak shape to improve our Rietveld refinement. What we'll do is we'll switch back to the slides, and we'll use the slides to just look at how peak shapes are described in the Rietveld refinement, and then we'll come back to the fit in a second. So let me come back to the slides and talk a little bit about peak shapes. So the approach we're going to take in this tutorial is to use an empirical peak shape to fit our powder diffraction pattern. And in an empirical approach, what we essentially say to ourselves is we're going to use some kind of a mathematical function that fits the peaks very well. We're not going to worry particularly about why that function works. And that's an approach that's used in lots and lots of Rietveld software. There is a more advanced approach called fundamental parameters, where you really think about the physics of the diffractometer and the sample and how those contribute to the peak shape. But we'll save that for a later tutorial. So when we're using empirical peak shapes, there are various different peak shape functions that come up in Rietveld refinement. Two of the most common are what are called Gaussian and Lorentzian peak shapes, and actually a mixture of those two creates what's called a Voigt or a pseudo-Voigt function. So Gaussian and Lorentzian peak shapes you're probably familiar with from other areas of science. What I've done on the screen here on the left is I've just shown you a plot of a unit area Gaussian peak shape and a unit area Lorentzian peak shape, just so we're familiar with what those functions look like. Now, Gaussian, as I say, should be familiar from other areas of science. It's a classic bell-shaped curve. And it's actually the shape that you'll have encountered, for example, if you think about normal distributions. Normal distributions are described by Gaussian functions. So it's a curve that tends to be relatively rounded at its top. At its full width at half maximum, so how broad it is at half its maximum intensity, its full width at half maximum is relatively broad, but then it falls away to zero relatively rapidly. So that's a Gaussian function in blue. If we compare it to a Lorentzian function in red, what we find is a Lorentzian at its full width half maximum, a Lorentzian is sharper than a Gaussian, so the full width half maximum is smaller, but it falls away to zero much more rapidly than a Gaussian function would. Okay, we can look at the mathematics of those functions. Mathematics don't matter very much for what we're doing here. If you want to see them in more detail, again, this paper on the right will contain that detail. But this at the top is the mathematical form of a Gaussian expression. This is the mathematical form of a Lorentzian expression. And the function that we use most commonly in empirical peak shapes with Rietveld refinement is what's called a pseudo-Voigt function. And it's a mixture of a Lorentzian and a Gaussian function. So you take some function of a Lorentzian, and in this case, we're going to sum it with some contribution of a Gaussian, and a quantity eta called a mixing parameter. It tells you how much Lorentzian component you have and how much of a Gaussian component. So the reason that Gaussian and Lorentzian functions are used so widely is that they do a reasonable job of fitting the peaks in a powder diffraction pattern. So what I've done on the slide here is I've just taken a single peak from the data set that we're looking at, and I've taken a peak at about 58 degrees 2 theta, and I've tried to fit it using a Gaussian function at the top. And you can see that the Gaussian function does a reasonable job of fitting the experimental data. If you look at it in detail, it's actually slightly too broad at the half maximum, and it falls away to zero slightly too rapidly. So it's not a perfect function to use. If we try and look at fit a Lorentzian instead, you can see that a Lorentzian does a better job of fitting the data. The R factor is lower. If we look at the Lorentzian fit, we can see actually it's slightly too sharp at the full width at half maximum, and it falls away to zero slightly too slowly. And in fact, if we take a mixture of a Gaussian function and a Lorentzian function, what we call the pseudo-Voigt function at the bottom, you can see that I do a really quite nice job of fitting the data if I take 68% of a Lorentzian function and 32% of a Gaussian, and I mix them together. So that's why we use pseudo-Voigt peak shapes in powder diffraction. Now that's fitting a single peak. Now what you'll have seen if you look at any experimental powder diffraction patterns, you'll know that the width of peaks, the full width at half maximum, often varies as a function of 2 theta. Typically peaks are relatively sharp at low 2 theta values, and they're much broader at high 2 theta values. And as I say, that's occurs from a combination of instrumental effects and sample effects. Just to give you an idea of the magnitude, for the data set that we're working with here on yttrium oxide, I've gone through the powder pattern and I've extracted the full width at half maximum for every reflection, and you can see that the peaks are sharp at low 2 theta and broader at high 2 theta. So we need to take account of that when we're fitting our empirical peak shape function. Now traditionally, at the top of the slide here, if you're using a Gaussian peak shape function, what's traditionally been used is that the full width half maximum has been described in terms of 3 parameters, u, v and w. And the dependence on 2 theta is given by this equation here. It's u tan squared theta plus v tan theta plus w square rooted. Okay, if we're using a Lorentzian function, typically the 2 theta dependence of the full width half maximum is defined by this second equation on the side. It's x tan theta plus y upon cos theta. So again, when we're working with these functions, the u, v, w, x and y are the parameters that we're going to refine. Just in passing, you might wonder why these particular expressions are used. It turns out for the Lorentzian component, the tan theta describes a strain contribution to the full width at half maximum, and the 1 upon cos theta describes a size contribution to the peak width. So those are things that, again, we'll come back to later. So those are the basic ideas of how you describe the dependence of the full width at half maximum on 2 theta. Again, in reality, the expressions used in real Rietveld software are slightly more complicated. We're going to use a peak shape function called the Thomson-Cox-Hastings pseudo-void, or TCHZ function. It's very similar to the ideas that we've just looked at. Turns out the Gaussian contribution to the full width at half maximum is given by this first expression here. It does contain u tan squared theta plus v tan theta plus w, but there's an extra term introduced, which is z on cos squared theta. The Lorentzian full width at half maximum component is given by x tan theta plus y cos theta. So again, u, v, w, x, y and z are your refinable parameters. The mixing coefficient, how much Gaussian and how much Lorentzian you have present, is slightly more complicated. It's given by this expression here that eta depends on a quantity q plus q squared plus q cubed multiplied by some parameters. And if you remember when we looked at the topaz.inc file earlier, I said, look at this line. It says pv underscore law depends on q squared and q cubed. This is actually the equation that we've seen already in the topaz.inc file. So if you need to check the mathematics, look in topaz.inc. So that's the mixing coefficient. It depends on this quantity q. Q itself is defined as the ratio of the Lorentzian full width at half maximum to the total full width at half maximum, and the total full width at half maximum depends on the Gaussian component to the fifth plus something times the Gaussian to the fourth, Lorentzian to the first, etc., etc. So the mathematical equation used when we're fitting peak shapes is relatively complex, but it is just fundamentally related back to these simple ideas that we talked about on the previous slide. Okay, so let's go back to our refinement and let's try to improve the peak shape in our fit. Okay, so let's go back to JEdit and go to the line which describes our peak shape. So our peak shape is described by this line here, TCHZ underscore peak type, and you can see that there are various parameters defined: a U parameter, a V parameter, a W parameter. I'm going through and I'm just setting these all to small values to start with: a Z parameter, an X parameter, and a Y parameter. So what I've defined there is the peak shape coefficients are all very small numbers. So if I send that to Topaz and I try and do a Rietveld refinement, you can see that the peaks are now very, very sharp functions. So let me stop that refinement and I won't, let me risk refining. Okay, so that's a very sharp peak shape. So here we can see that the experimental peaks are much broader than the peak shape is describing. So let's try playing with the peak shape coefficients to improve the fit. Well, one coefficient that was very simple that we looked at was the W parameter. W described a constant Gaussian full width at half maximum as a function of theta, at least to a first approximation. So let's just try changing this value W to 0.1, sending that to Topaz and trying to do a least squares refinement. So can you see what's happened now? We've got peaks which are actually much broader than we would expect, and they're broad over the whole range to theta. So let's go back to my JEdit file And let's just try changing these values to a slightly smaller number. Let's make it 0.03 and send that back to Topaz and have a look at the refinement. And we can zoom in again at high angle, and you can see that the peak shape is now doing a much better job fitting the experimental data. So let's go back and try refining some of the other coefficients. And what I'll do is I'll actually turn on the U coefficient, the V coefficient, I'll refine W, and I think we can be brave and refine the Lorentzian terms, the X and Y, at the same time. I'm not going to refine the Z parameter. It turns out it's highly correlated with the other parameters. We'll come back and look at that in a second. So let me send that over to Topaz. Let's switch to Topaz, redo the refinement. And can you see now that the peak shape is actually doing a really nice job of fitting the experimental data over more or less the whole 2 theta range. Now, in fact, if we look at the peak shape, if we look at these low angle peaks, can you see that experimentally the blue data here is actually asymmetric? It's got this large tail on it, which our empirical peak shape is not picking up. Now, that asymmetry is actually caused by beam divergence in the diffractometer. It's actually related to the width of the beam as it hits our sample. It's called axial divergence. And in Topaz, we can correct for axial divergence by one simple parameter, which is this axial term, which we had fixed to 0 when we started the refinement. So, as I say, it describes the physical width of the beam as it hits the sample. Let's just try changing that value. Let's make the width of the beam on the sample 20 millimeters. Let's see what influence that has on the refinement. So if I just do a single cycle of least squares, can you see what's happened with a beam width of 20 millimeters? Is I've got this broad asymmetry on the peak. That value of 20 is clearly too high. So let's stop the refinement and let's go back to a smaller number. Let's try a value of 10 millimeters, which I know is almost correct for my diffractometer. And let me turn that parameter on to refine. Let's send the refinement back to Topaz. Let's do a single cycle of least squares so we can see the effect of a 10 millimeter asymmetry on the peak. You can see now that the asymmetry is described rather nicely, but the peak has actually shifted in 2 theta. Remember when we talked about 2 theta aberrations, asymmetry can shift the maximum of a peak. So now we're describing the asymmetry properly. Probably the 0 point or the cell parameter the sample will need to refine a little bit. So let's do the refinement, and we've got an R factor now 14.86%, and we're doing a pretty good job of fitting the peak at low angle. And if I come back to high angle, we do a pretty good job of fitting the peak shape at high angle as well. Okay, so what's now wrong with our diffraction pattern? It looks a pretty good fit, but if we're being really critical, possibly we might say, if we look at the difference curves, that all of the peaks at high angle are slightly undercalculated. Can you see that this red curve is slightly lower than the blue curve? So that's occurring on all of the high angle peaks. So it looks like there's an effect which is influencing the intensities as a function of 2 theta. One parameter that we've looked at already that does that is, of course, the temperature factor. Maybe we need to refine the temperature factors on the individual atomic sites. So let's come back to our refinement and try and turn on the temperature factors. Now, the temperature factors are stored at the end of the lines here, and these B equivalent values. So what we want to do is turn on all of the temperature factors. Now, previously, when we've been column editing, all of our lines have been nicely lined up, and we've been able to just highlight a set of values in the file and type over the top of them. One of the things that happened here is that everything's got out of alignment in JEdit. There's a little trick. If we go to macros, spaces align, hopefully, yeah, the sight lines have got beautifully lined up in columns again. So I can come to the end of the line and I can turn on to refine all of the temperature factors. So let's send that back to Topaz and do the refinement again. And now we find that our R factor is 14.134%. And if we look at high angle, you can see that we're doing a really pretty good job at high angle too. So this is probably a really nice Rietveld refinement at this point. One of the things it's useful to do at the end of a Rietveld refinement is, as well as to look at the data on a normal linear scale, it's always worth looking at the data on a square root scale to see the quality of the fit. A square root scale is useful for a couple of reasons. One is that it lets you see the weaker features in the diffraction pattern of the material more closely to make sure that you're doing a good job of fitting the strong features and the weak features. The other thing is that the way the statistics work in a Rietveld refinement is, if your model is good at the end of the refinement, the difference curve on a square root scale should be randomly scattered around 0 with no systematic errors in it. This is probably a good Rietveld refinement. We can see that the R factor here is 14.134%. If I go back to JEdit, then that R factor is written at the top of the JEdit input file. And over on the right here, we should be able to see the goodness of fit of the refinement. Yes, so the goodness of fit of the refinement is 1.19. Remember we said that the goodness of fit, or chi-squared, should tend towards 1 at the end of a Rietveld refinement. So this is probably an appropriate experimental model. So just in finishing up, what else should we do? Well, one of the things that we should do in finishing up is we should just look at the standard uncertainties on our refined parameters, the errors on them, if you like. So Topaz has got a little flag called do errors, which calculates the errors on our refined parameters. So if we now do the refinement in Topaz again, and we switch back to our input file, we should find that each of the parameters that we're refining, for example, the cell parameter, has got its standard uncertainty appended in blue. So one of the things we should do is make sure that those standard uncertainties aren't too large on any of the parameters that we're interested in. The other thing that gets written to the input file is what's called the variance covariance, or the correlation matrix, and it tells you how the value of one parameter depends on another parameter. So in the input file, the parameters are listed in order, and the correlation matrix is shown on the right. So this is a little bit hard to see in JEdit, but fortunately, if we go back to Topaz itself, if we click on this little correlation matrix button and we run a refinement, we actually get a nice visualization of the correlation matrix on the screen, and that's often easier to look at. So if we look at the correlation matrix, what each of these entries does is it tells you how the value of one parameter is correlated to the value of another parameter. So for example, this number 59 here is the correlation between the 0 point and the axial divergence term. So both of those influence the peak positions. And what you should be looking for in your file is that none of these correlation coefficients are larger than, say, something like 90% or so. If you see large terms in here, then you ought to be concerned. One of the things that we talked about at the start of the tutorial was things, particularly we mentioned that site occupancies and temperature factors might be quite highly correlated parameters. So we can explore that with our input file. Let's just say to ourselves, let's go and set the 2 theta range in our pattern so that we don't refine all of the data. Let's just refine out to a 2 theta maximum value of, say, 70 degrees. So we can put finish X 70 degrees. And now when we do a Rietveld refinement, let me minimize the correlation matrix. When we do our least squares refinement, I'm now only fitting the data out to 70 degrees. And then let's go back into JEdit and let's try refining the site occupancy of the oxygen 1 site, which is this term, the occupancy. Let's try refining that parameter at the same time as the temperature factor, and let's see what we see in the correlation matrix. So if I do my refinement, my R factor is 12.694. The R factor actually decreases a little bit when I try and refine both of those parameters, but if we look at the correlation matrix, we see that these two parameters are actually quite highly correlated. So if I click on the correlation matrix, the correlation coefficient between the temperature factor and the occupancy that we're trying to extract is 90%. The other way we can explore correlations is to go back to the input file and actually fix some of the parameters and see how much the other parameters are affected by. So as we said, the R factor at the moment is 12.69%. So let's just go back to JEdit and let's say to ourselves, well, let's just fix the oxygen occupancy at 0.9 and see how much our R factor changes in the refinement. So just for note, the temperature factor is 0.5 angstrom squared when the site was essentially fully occupied. Let's come back to Topaz, do the refinement again, and what we find is that when we did that refinement, the R factor started at a high value, something like 13.5%, but then came down to 12.8%, which is essentially the same as we had previously. If we come back to the input file, we can see why. What's happened is the temperature factor, the value of the temperature factor, has compensated for the change in the occupancy. So as we said at the beginning of the video, if the occupancy value is too low, the temperature factor becomes smaller to compensate for that. If the occupancy factor was too high, temperature factor could become higher to compensate. So with real diffraction data, where we might have a more complicated model and there could be other experimental artifacts, we have to be very careful about refining temperature factors and site occupancies at the same time. We should only do it if we've got very good quality data over a large range of 2 theta or perhaps neutron diffraction data. So let me return this file to the state it was in before. Let me put the oxygen back to full occupancy of 1, and we'll refine the temperature factor, and I'll just go back to the full 2 theta range that we were looking at previously. So we're back to the refinement that we had before. So the refinement that we had before, we've got an R factor of 14.134%. The other place that I just wanted to look at correlations was in peak shapes. You remember that I said that when we refine peak shapes, I chose not to refine the PKZ peak shape. So I kept the PKZ coefficient fixed at 0. And the reason why is it turns out that the PKZ peak shape is actually highly correlated. In fact, it's infinitely correlated with other parameters in our peak shape. And we can see that by, if we try and refine the PKZ component of the peak shape, send that back to Topaz, we do our Rietveld refinement. The R factor here hasn't changed, it's 14.134%. But if we look at our peak shape parameters, can you see now that we've got some really large correlations in our peak shape? So the PKZ value, which is row 21 in our correlation matrix, it's highly correlated to the PKU value and also the PKW value. In fact, it's 100% correlated, and that tells you that you can't get independent information on U, W, and Z simultaneously. We can see that again by, if we go back to the input file, and instead of refining the value of Z, let me take the value of Z, and it was fixed at 0. Let me just try taking that value and changing it to 0.1. Now, because we've changed the peak shape coefficient, it ought to change our diffraction pattern. And if we do the refinement, we'll see that, yes, the changing the peak shape value does change the refinement significantly. But if we do the refinement to convergence, everything's working perfectly. I may not be in exactly the same minimum, but I've come back to an R factor, which is essentially the same value, 14.3%. And if I go back to JEdit again, and this time I change my value of the peak shape to 0.2, we're going to see exactly the same thing. Just for note, when we're doing the refinement here, have a look at this value of PKW. It's minus 0.096. When we do the refinement again, we've changed PKU, so the peak shape is different, but we do the refinement and we come back to essentially the same R factor. What's happened in the input file is that the value of W and in fact the value of U have both changed to compensate for this new value of Z. So essentially, because there's infinite correlation between those 3 parameters, I choose never to refine the Z component of the peak shape and keep it fixed at 0. So that's the model that I would choose to use. Okay, so at that point, I think we've done all of the standard things that you would normally want to do in a simple Rietveld refinement. I hope that going through it in this steady step-by-step fashion has been useful and has taught you some of the do's and don'ts of Rietveld refinement. As I say, we'll have some follow-up videos on this, which will explore a couple more specialist things that you might want to do with this particular example. If you want more information about any of the things we've talked about in this video, you might find some of these resources useful. At the bottom are a couple of general resources on powder diffraction and Rietveld refinement, and at the top are some more Topaz specific resources. You might find the Topaz web tutorials useful, which are on my web pages. The link is at the bottom of the slide here, but if you just do a Google for Topaz tutorials Durham, you should hit that site. There's also a link to the Topaz wiki, which contains lots of information about Topaz and how it works. And there's also a link to the Topaz forum where you can ask questions about Topaz, and hopefully one of the experts from around the world will answer those questions. I really recommend you read this document here. If you look in your main Topaz directory, there's a file called technicalreference.pdf, and that's written by Alan Coelho, and it's got details of all the functionality of Topaz and the mathematics of how Topaz works, so you should really try and read that document. If you want something more general, you could try this textbook on the right called Rietveld Refinement. It's written by Robert Dinnebeer, Andreas Leineweber and myself, and it contains the background theory of Rietveld refinement, and it also translates that theory into Topaz syntax, so you can make the link between the theory and actually doing refinements in Topaz. If you want something slightly more straightforward, you could try this article at the bottom in the Journal of Chemical Education. What we do in that article is again tell you the fundamentals of Rietveld refinement, but then we teach you how to do a Rietveld refinement in Excel. So you get to type in all of the equations that you need, and it teaches you how Rietveld refinement actually works. So hopefully some of those resources will be useful. Finally, I'd just like to thank a few people. I'd like to say thanks to Alan Coelho and to Arndt Kern. And then I'd like to thank my various students and collaborators over many years for all of the exciting challenges they brought in powder diffraction and Rietveld refinement. And finally, thanks to you for watching this video. And again, I hope it's been useful.